Chapter 2, Section 3 is all about falling objects. First thing for us to consider is look at this ball that Bob is holding. Pardon me. While the ball falls, please, number one, describe the speed of the ball as it falls. So as the ball falls, in the beginning it's going slow, and then as it falls it will become faster, and at the bottom it will be going the fastest. You could say that the ball accelerates as it falls. So what do we call something that is just falling? The vocabulary word you'd use is called free fall. What has to be true in order for free fall to take place? There are two criterion that must be true in order to have free fall. Number one is you must have gravity. Obviously, things fall because of gravity. We'll get into the details on that in a later time, but just for right now, our understanding is that things fall because of gravity. Second, to be in true free fall, you must have no air resistance. When doing the problems in our book, please consider there to be no air resistance unless it is specifically mentioned. So, if the ball is going faster and faster, we can say that it is accelerating. What is the acceleration of gravity on Earth? On Earth, things accelerate at negative 9.81 meters per square second. This is the acceleration of gravity. We typically just call it g. Notice that it is negative because the acceleration is down towards the ground. This becomes significant, especially when you throw things up in the air, because then as the thing goes up, it's accelerating downward, so it slows down while going up. Once it reaches the top, it begins to accelerate downward, and it speeds up back towards the bottom. We have a couple equations that are very convenient for us to have here. Number one, how fast something is going during a fall. I call this free fall how fast. At a given, what is the velocity at a given time? Now, if you know that something fell for 5 seconds, you could put 5 in for time, and you could put g in, negative 9.81. 5 times negative 9.81, if we round that to 10 for ease here, we would say it would be going roughly 50 meters per second downward, negative. And that's how that equation works. You can use it for a time somewhere in the middle of a fall, or you can use it for the time at the end of a fall. The other equation that is one of my favorite equations, actually, is to tell how far something has fallen in a given time. So, delta y equals 1/2 gt squared. At a given height, or from a given height, it will take a certain time, or if something falls for a certain time, it will go a certain distance downward. Very convenient. Understand, if you're using Bob dropping the ball as your sample, if he drops the ball from, say, 25 meters up, and you want to do this kind of thing, you have to say negative 25 meters, because it's going to fall 25 meters down, and then you'll get the proper time. Otherwise, you might be trying to square root a negative, and you might get a little frustrated there. All right, this is accompanied with a homework assignment on page 60, 1 through 4. In number 1 on page 60, you're on Mars, actually. So the acceleration of gravity on Mars is only 3.7 meters per square second. So you can use that in place of the g. And they ask, if you drop this thing with that acceleration of 3.7 meters per square second, and you drop it, I believe, 239 meters, how fast will it be going when it strikes the ground, and how long will it take to strike the ground? You could use these two equations to do this. You could put in negative 239 meters into the height, calculate the time of the fall. Then you could use that time for the second part to calculate how fast it's going. If memory serves, that's 42 meters per second is the speed. I cannot recall the time from my memory. In problem number 2, it's kind of like Bob here. There's a flower pot. It falls 25 meters. Again, they want to know how long does it take and how fast is it going, although they ask in reverse order. Time is like the most important thing to worry about here. Time links everything else together. So what I would do is I take my 25 meters here and solve for time. Then I take my time and solve for the velocity. Number 3 is a different sort of question. If we take our ball, I got to make a new ball. If we take our ball and they say in number 3, our ball is thrown up with a velocity of 8 meters per second. How fast will it be going when it returns to the hand? Well, if the acceleration of gravity is what's slowing it down from 8 meters per second to 0 up at the top, then the acceleration of gravity is also what speeds it back up from 0 back to 8 meters per second. If you'd like to solve and test this, you could put in the VF squared equation, where VF is what you're searching for. You could have VI as 8. You could have then 2, so it's VF squared equals VI squared, plus 2a delta x. Well, the a will become g, the x will become a y. And really, if we're looking for the speed here, and here's the initial, you'll notice it's not going vertically anywhere in the ball. So that means that your height would be 0. So if you put the height in for 0, and you will show mathematically that the velocity there will end up being 8, just like it is the other way. And then in number 4, they say you got this volleyball. It has initial velocity of 6, and then they hit it upwards. How high did it go to get to a speed of 1.1 meters per second upward? So it's before it reaches the peak in its height. So again, you can use that VF squared equation again. VI is given in the sample problem on the previous page. VF is given on the homework, and delta y is what you solve for. All right. Good luck.